Mr. B. Dhanasekar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharathidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We are having the subject theory of computation. As far as the previous episode is concerned, we have learned how we are simplifying the grammars. So actually we will be given the context-free grammar where the productions are all of the form A derives that is alpha, and A is a single variable followed by the right hand side is having that is alpha, where alpha belongs to the variable or terminal any number of times including epsilon. But we know that the alpha, that is the right hand side, can have any number of symbols, but it is possible to simplify the grammar most of the time provided the language is not having epsilon but the grammar has epsilon. That is a production with the right hand side having epsilon means, so it is strictly needed to have a production with the epsilon only if the language includes epsilon. Suppose if the language does not include epsilon, then having a production with the epsilon as the right hand side is certainly going to increase the number of steps required for recognizing the string rather than that is introducing any benefits for the that is compilation steps. So that is the reason why when you are knowing that the language does not include epsilon, we will remove all the productions where the right hand sides are having epsilon. That is, we call them as epsilon productions. So that's the first one we had seen, and the next one is the elimination of the unit productions. So an unit production is going to be that is A derives B of the form. So where A is a variable and B is also a variable, that is the left hand side is having a variable which will be in turn during the derivations replaced by the another variable. So except going for the more number of steps, as far as the essential form is concerned, that is the string which you are going to parse is concerned, it does not introduce any kind of progress. So just because of having a production of the form that is unit, more steps will be involved, but it won't ensure the progress in your recognition of the string. So it is possible to eliminate these kind of unit productions from the given that is context-free grammar so that the number of steps required for recognizing the string can be reduced. These are the two steps we have already seen. So now if you are very sure that the production given for us, that is the context-free grammar, does not have any kind of useless symbols, and it is not having the unit productions, and it is not having epsilon productions, then we can convert it into that is a form called Chomsky normal form, where the productions are all of the form A derives that is BC, where B and C are variables and even A is also a variable. The right hand side has exactly two number of variables, or it is going to be a single terminal, and that part also already we have seen. As far as today's episode is concerned, so we are going to have once again the context-free grammar is given for you, which does not include that is useless symbols, unit productions and epsilon productions. Now this is to be converted into another form of the context-free grammar called Gribak normal form, or which is going to be GNF, and which is going to take lesser number of steps than the number of steps required even for with the help of the context-free grammar in Chomsky normal form. So first we should know that is what is the format of the Gribak normal form. So it's once again a context-free grammar where the productions are of the form A derives alpha, but the right hand side should always start with the terminal. That is a condition for calling a grammar as Gribak normal form. So a grammar is said to be in GNF only if the productions are of the form A derives small a followed by alpha. That is the right hand side, if you are having more than one symbol, that is then first symbol is strictly supposed to be a terminal followed by any number of symbols either in the form of variables or terminals. And if you have only one symbol on the right hand side, then it should be exactly a single terminal, so that we will be able to ensure that the number of steps required for recognizing a string is going to be the linearly proportionate to the the number of symbols available in the actual string which you are recognizing. So that part we will see later, that is how many number of what is the relationship between the number of steps and the number of symbols available in the string which is to be parsed. So now to come go for the identification or the generation of the Gribach normal form from the given grammar, this given context free grammar which does not have unit productions or epsilon productions or even useless symbols. The first thing to be studied is how we are identifying whether a grammar is left recursive or not, and if it is going to be left recursive grammar, how do you solve that? First you should know what is the meaning of a left recursive grammar. A grammar is said to be left recursive if it is having a production of the form A derives A alpha or beta. So we can find that the left hand side has A, and even the right hand side it starts with A. So what happens here is, a variable when it is expanded, it is once again introduced in the same variable, but where it introduces is on the leftmost position of the derivation or the next step of the sequential form. That is what this production says, that is A is expanded to A alpha, and strictly it is required to have another production that is non-left recursive, which is of the form beta, where beta does not start with the variable on the left hand side. So this beta is mandatory. If beta is not there in the production, then definitely this grammar becomes an useless grammar which will not be able to recognize any string of its own, because of every time this A introduces A and there is no further replacement for A. So if you are having a production of the form there is A derives A alpha or beta, and because of this A derives A alpha, we call this production as a left recursive production. And the problem with your left recursive production is when we are expanding or constructing the tree in a top down fashion. So the compiler can parse the strings either in bottom up approach or in top down approach, and if the top down approach is followed, then we start the construction of the tree from the root of the tree, and the root of the tree, if it is labeled with that variable, and if that variable is every time introduced on the leftmost subtree, so we will be trying to expand only the leftmost subtree, and we will try to find out whether there is any matching and there is pattern obtained from the string which is to be passed or not. But here there is no point in making a match, because every time the leftmost symbol being introduced is going to be a variable, and that too it is a variable which is on the parent position, so it is going to be in infinite loop. So every left recursive production, if they are expanded continuously, then the process of expansion will be continuously going or infinitely going without consuming even a single symbol from the input. It means that it will not ensure any progress on the recognition of the string which is supposed to be parsed. So if you have left recursive grammar or left recursive production, the top down parser will be definitely in trouble, because it will not produce any kind of progress in the recognition of the string. So it is strictly required to remove these kind of left recursive productions from the grammar. So once they have removed from the left recursive grammar, then we will be able to ensure that the same language is going to be recognized, but at the same time the grammar is not going to be left recursive. That means if we are having a production of the form A derives A alpha or beta, it must be rewritten into a different form without changing the actual language being recognized, so that it is not going to be left recursive anymore. So now we shall see that is how we are recognizing or removing the left recursion available in the grammar. So here is a production we have, that is A derives A alpha or beta, which is left recursive. So now we are going to rewrite this production in this way. Definitely this A is going to recognize beta, so I will be writing A derives beta, and sometimes if it starts with A, there is A alpha, it will be continuously generating, that is A followed by A alpha, A followed by A alpha, A followed by A alpha. So the actual pattern is going to be beta followed by alpha to the power n is the actual pattern to be recognized by this particular production. Beta followed by, there is one beta, that is at some stage definitely we must replace this a by beta so that there will be an end for the that is derivation process, derivation. So it is going to be beta followed by alpha to the power n. So any number of times we can recognize the alpha, or we can introduce the alpha in our pattern. So now to create the continuity, we will be introducing the second alternate for a. It is going to be beta followed by b, which is a variable. So far it is not there in the given grammar, and this time we are introducing it just for connecting the recursive production. So a derives beta or beta b followed by b derives. So b may derive there is at least one alpha or any number of alphas. So the introduction of this b production ensures that the alpha can be generated as many times as we wanted to have. So if you want to have exactly once, then it can straight away go for b derives alpha. And if you want to have two number of times, then you can go for the second alternate first of all. So b derives alpha b, and then b can be this time expanded by using the first alternate. So we will be having two number of times alpha, and already we know that beta has been already generated. So beta followed by alpha, alpha will be the answer. So every production of the form, that is a derives a alpha or beta, will be rewritten as a derives beta, where beta is going to be a non-left recursive component. So that is very important, non-left recursive component, and followed by, we will be having that is beta followed by b, and this b is once again written with alpha or alpha followed by b, which is meant for that is iteratively generating as many number of times as we want to have that alpha. So this is a solution for that is rewriting the left recursive productions with no left recursion, and this could be expanded for even that is larger productions also. So to say in general, when we are having a production of the form, that is a derives a alpha 1, a alpha 2, etc. up to a alpha r, that is we have r number of left recursive rules, and in all the rules, that is all the r number of rules, we find a is in the beginning. So a derives a alpha, once again a derives a alpha, then once again a derives a alpha like this, and there are some number of that is non-left recursive rules also available for that. So at least there should be one, or we can have any number of non-left recursive rules. So in this generalized format, we are having s number of non-left recursive rules as stated here. It is beta 1, beta 2, etc. up to beta s. This is what the given production. So now we should go for rewriting this production so that the new grammar is not going to have any left recursive rule. So what will happen is, first you write the a production with all the non-left recursive components. So we have, there are s number of non-left recursive components, which are beta 1, beta 2, etc. up to beta s. So put them in the order, beta 1 or beta 2 or beta 3, or finally it is up to beta s. Or, so now we are thinking about the connectivity, as many number of times as we wanted to have that alpha. So that is needed. So for that, once again we will introduce the same set of productions, beta 1 to beta s, along with the suffix called capital B, and capital B is going to be the non-terminal which we are introducing for generating the alpha as many times as we wanted to have. So beta 1 followed by B, so that this B can have that is anything like alpha, and then beta 2 followed by B, beta s followed by B. So it will be exactly one variable being introduced, and that variable is introduced as the suffix of all the non-left recursive components. The non-left recursive components are beta 1 to beta s. Now to expand this B, we will be writing the rest of the recursive component. That means we are having r number of left recursive rules, alpha 1, that is a alpha 1, a alpha 2, and finally up to a alpha r. So now that is after removing the left recursive component, the left recursive component is a. After removing this a, we will be having alpha 1 or alpha 2 or alpha 3 or etc. up to that is alpha r. They are all introduced here now. So B derives alpha 1, alpha 2, alpha 3, etc. up to alpha r. And if you are that is in need of exactly once that alpha I, no problem. But there is a need for generating that is alpha I any number of times. So it's required to have connectivity. So alpha 1 B, and then alpha 2 B, and then it is going to be alpha r B. So A derives beta 1, beta 2, etc. up to beta s, or beta 1 b, beta 2 b, etc. up to beta s b. Then B is alpha 1 or alpha 2, etc. up to alpha r, or alpha 1 b or alpha 2 b or etc. up to alpha r b. So this is what the grammar after generating the non-left recursive components. So given a grammar which is left recursive, it is required to remove the left recursive component so that this grammar will not go for that is infinite, that is loop, without consuming any symbol from the input. So that is about the left recursion elimination. After a short break, we shall continue with the remaining part of the lecture. Welcome back. We have just seen the method being used for generating a non-left recursive grammar from the given left recursive grammar without changing the actual meaning of the grammar. Actual meaning, I mean, that is the language recognized by the grammar. Let us see one simple example about that is how a grammar is left recursive and how it will be eliminated so that the new grammar is non-left recursive without modification on the exact language being recognized. So here is an example. This is an example taken from the expression grammar. We have that is E derives E plus T or T. So expression is an expression plus another expression or a term, and the T is going to be expanded by using that is T derives opening bracket E closing bracket or that is ID. So these two are the productions we have taken, and the second production does not include there is any that is left recursion, but whereas the first one is having left recursion because T derives that is E derives E plus T or T. So the E is the variable on the left hand side and which is there once again available as the first symbol available on the right hand side. So the grammar becomes left recursive. So now we need to rewrite the first rule without left recursion, whereas second rule need not be disturbed, because the second rule does not include any left recursions as it is starting with a terminal for the first alternate, and even the second alternate also we are having both that is terminals. So no need of bothering about that. Whereas in the case of first rule, we find E derives E plus T is the rule. So the left hand side and right hand side are having same symbol in the beginning. So we should go for rewriting the that is production without left recursion. So as per the that is method being used for converting it into the non-left recursive grammar, we find that the non-left recursive part of this grammar is T, or this production is T. So first we will put it as T, E derives T, and then for the connectivity process, that is for generating that alpha as many times as we wanted to have, we will go for introducing a new variable called E prime. So E derives T or T E prime, that is the first rule. The second rule is we should go for expanding this E prime. So what this E prime denotes, or what is going to the right hand side for this E prime. So this E prime is the rest of the left recursive component. The left recursive component is E plus T, the rest of left recursive component is plus T. So we will go for writing that as plus T first of all. Then for generating this plus T as many times as we wanted to have, once again the connectivity is needed, that is an iterative procedure is needed. So we will go for writing plus T followed by E prime, which is same as the E prime which is available on the left hand side of the rule. So as a result of eliminating the left recursion from E derives E plus T or T, we have two more productions. So the answer is E derives T or T E prime, and E dash derives plus T or plus T E prime, and the final rule is not at all disturbed. You are having T derives opening bracket E closing bracket or that is ID. So this is how we are eliminating the left recursion from the grammar. So now we should go for that is converting the given that is grammar into the Gribag normal form. So the first thing is we should go for ordering the that is grammar given for us. So in some that is increasing order of the production that is which are available on the that is variable, that is a variable list. So we are having the variables list which is V. We have n number of symbols. We have some ordering. So A1, A2, A3, etc. up to there is An. So the ordering is supposed to reflect the order in which the productions are returned. So A1 is the first production and A2 is depending on A1, and A3 is depending upon both A1 and A2 or not, and even A4 is depending upon either A1 or A2 or A3 or all the three, like that. And similarly, when you go for the last one, there is An, it will be depending upon A1, A2, A3, etc. but not necessarily be depending on all. So this is what the order in which we are listing the productions. So now we will be having the productions. So once it is listed, we will be having these productions satisfying this condition. One is AI derives Aj gamma for all I less than j. It means a variable which we have already that is having, that is Ai, and now it is going to start with a variable which is new for us. So A1 derives A2 alpha, something like this. So A1 derives that is A2. The condition is I less than j. So we need to have the productions in this order. A1 derives that is A2, or A1 derives A3, or A1 derives A4, like that, followed by this gamma. So we are concerned only about the first variable. The rest of the things can be simply that is ignored, because we are looking for whether there is any left recursion available or not. If there is any left recursion, they should be removed. So in this case, we find that is Ai is deriving the right hand side with a terminal with a variable called Aj, which is higher in order as far as that listing is concerned. But this may not happen always, because every time if you introduce a new variable on the right hand side, the grammar will be useless grammar. So there is a need for having at least one or more production, so that the right hand side is going to start with a variable which you have already encountered or which you have already listed. That is, we are going to find out some k such that your ak derives aj gamma such that there is your condition is k is greater than j. That means this time we have a variable whose index or whose order is going to be greater than the order of the variable which is available on the right hand side's first position. So ak derives aj gamma. So now what can be done is, since this Aj has been already encountered or already listed, we know what are the various productions available for Aj. So we can go for substituting this Aj that is in the productions for Ak. So Aj has some number of productions or some number of alternates, and everything should be substituted in the place of Aj wherever we are having the rule called Ak derives Aj gamma, where k is greater than j. And this substitution may happen at most, that is k minus 1 number of times, because we find that kth symbol is on the left hand side and the right hand side is going to have an order of that is j, which is less than k. So the number of substitutions we can go at most k minus 1. That is, if you replace that is every variable by its previous variable, the replacement may go up to that is k minus 1 number of times. So after doing all these substitutions, so we should go for we will be having a situation like that is k is going to, that is your ak derives am gamma, where k less than that is m. That is one format of the production, and where this k is equal to m is possible. As long as we find that ak is deriving am alpha, so gamma, where k is less than m. But if we find that k is equal to m, then the productions are going to be left recursive. The situation is going to be ak derives ak gamma, which is a left recursive production. So now what should be done is, we should go for that is removing the left recursion from the grammar. Then after removing the left recursion from the grammar, we will be able to rewrite the grammar so that we will be having the new grammar with no left recursion at all. So the steps are, first you find out that there is productions of the form ai derives that is aj gamma, where j is greater than I, which means that j is going to be a new variable, and at some stage we will find a situation where your ak derives aj gamma, where your k is going to be having an order greater than the j. In that case we must go for substitution. So these aj's are all replaced by their previous ordered variables. Maybe it is aj minus 1, aj minus 2, like that. And that substitution may go up to that is k minus 1 number of times, where k is the order of the variable which is available on the left hand side. So now after all substitutions, we will be having the productions of the form that is a k derives some a m gamma where k is going to be less than or equal to m. So if it is less than or equal to m, no problem, less than no k, no problem, but if it is equal, then we will find that there is a left recursion available. By substituting the procedure for left recursion elimination, we will be rewriting the grammar so that the grammar will become that particular production will become a non-left recursive production. And do this as long as it is possible, and at the final stage we will be finding the entire grammar is free from left recursion, so that the grammar is called a non-left recursive grammar, which will be really useful for us for performing the Gribak normal form conversion. So this is the conversion step. So here we have an example. The grammar we have taken as S derives AA or 0 and A derives SS or 1, and from this grammar actually we do not find out any kind of left recursion anywhere. We see that there is S is deriving A or 0 is terminal, no left recursion, and A is deriving S or 1. So S is a variable which is more, that is other than the variable on the left hand side, so no problem, and 1 is going to be a terminal. But what will happen is we will be subjecting this grammar for the substitution. In that case, we will be taking the second variable A, whose right hand side starts with that variable which you have already listed. So in that case, we will be having that is the replacement for this S. So S has two number of alternate rules. One is AA, another one is 0. So in the place of S, we will be substituting both AA as well as 0. So you will be having the new grammar A derives AA followed by S or 0S, or it will be 1. So those are the resulting grammar obtained after the substitution. So now we need to find out whether there is any left recursion available or not. So yes, we have a left recursion. A derives AAS is left recursive, 0S is non-left recursive, and even 1 is also non-left recursive. So we should go for eliminating the left recursion now by rewriting this grammar. So as far as this particular grammar is concerned, we know that the first rule is left recursive, the second one and third one are non-left recursive. The first rule is of the form A derives A alpha, the second is of the form A derives beta 1, third one is of the form A derives beta 2. So after eliminating, we will be having A derives the beta 1 component, that is 0S, the beta 2 component is 1, and the connectivity beta 1 followed by B and beta 2 followed by B, that is 0SB and 1B. The next is writing the production for B. So for B, we will be having the non-left recursive component of the left recursive rule. So that is, after eliminating this A, we are having only this AS. So this is going to be introduced here. First it is B derives AS, and the second one is we will be having B derives AS followed by B once again for that is iteratively generating this AS as many times as we wanted to have. So now we have a rule of the form B derives AS, which is not looking the left recursive because of we find that A is on the first position, but A is not on the that is left side. The left side we have a B, the right side we have a A, so they are not going to be left recursive. So if both B are introduced on both sides, or is A is introduced on both sides, then there will be left recursion. So now there is no left recursion. So this time we will be having the grammar which is of the form the first rule is going to be S derives AA or 0. The second rule is A derives 0S1, 0SB or 1B, and B derives AS or ASB. But still we find that the grammar is not, that is Gribak normal form, as we find that is S is starting with a variable called A, and B starts with a variable once again AA. So we should go for the substitution now. So when you substitute that, we will be having the A substitution. So we will be substituting the value for A here. It is 0S, 0S here, and 1S here, 1SB here. And after doing the substitution, we will find all the that is alternate rules for B are starting with the terminal. So it is starting with terminal 0 and 0 to 1, 1. So all the rules. So now the same story is to be repeated for the roots of the first symbol, that is starting symbol of the grammar, that is S. Actually we are starting with the A here, but instead of A you substitute all possible rules for A. So we will be having S derives 0S followed by A, 1 followed by A, then another one is 0SB followed by A, then 1B followed by A, and finally we are having 0. So this is what about the answer grammar, that is the grammar which is in Gribak normal form. So we see that every rule is of the form a raised small a followed by that is alpha, that is every rule is starting with the terminal. So now if you look at the advantage, so if it is going to be a grammar in that is Gribak normal form, we find that that is every derivation for a string of length L will be taking exactly that is L minus 1 number of that is L number of steps, or if you are having the string length of n, then n number of steps are really required for recognizing a string. Without that it is not possible. That is, if you are having grammar like this, then definitely we need that is to have at least n number of steps, since we are introducing one terminal at a time. So that is the advantage of having the Gribak normal form. So to summarize, we have seen that is how the left recursive protections are handled, how we are removing left recursion. Then we have seen that is how the that is left recursion which are available in the indirect form are removed after substitution, then bringing the that is left recursion into the that is clear form and replacing that left recursive rules by non-left recursive rules. And then we are introducing the Gribak normal form and how the grammar has been converted into the context-free grammar in Gribak normal form. And finally, we have seen what is going to be the real advantage in going for the Gribak normal form. So as far as the questions are concerned, so the definition for left recursive grammar and how this left recursion is going to be eliminated from the given grammar, and how do we convert this into the Gribak normal form, and finally what is going to be the real need for the Gribak normal form, or what kind of advantage we will be having from the Gribak normal form. So that's about this particular episode. Thank you all.